manufacturer of test and measurement instruments located in Riga, Latvia. So hello from sunny and cold Riga. Spring hasn't really come this year yet. And what we do is we implement our devices and our solutions in automotive, aerospace, research, and other industries. On the slide, you can see the main pluses, the main advantages of Ruler. Among them are free software update, the customized tailor-made solutions, lifetime compatibility along warranty periods, online and on-site installation and training, free online support and education, and the fact that our equipment is extremely versatile, so it can be a vibration control system, for instance, a data acquisition system, a calibration system, all in one. And here's what we're going to talk about today. We'll talk about the reasons, or possible reasons, why we would like to move on from the classical triad of sine, random, and shock. And we will talk about some features that are already in your very well familiar sine, random, and shock, and also when you need these features and how you'd use them. So this is the idea of today's webinar. Initially, we thought we'd also move on to other test types that you may want to add immediately after sine, random, and shock. But as we were preparing, we realized that there's so much within sine, random, and shock module that you can do. If you already have these three basic modules, there's a lot of ways you can expand, a lot of ways you can modify and improve your testing practices. So we basically decided we were going to split topic into two. First, we'll talk about the subsystems of sine, random, and shock, so how you can advance those. And only after that, in our next chapter, next episode of the webinar, we will also talk about the other modules that you may want to purchase, you want to acquire after you have mastered sine, random, and shock. Okay, so we're almost ready. I think a lot of people have joined already, and let's go to the introduction where we discuss, the reasons.
Yeah. So I think we're ready to start. So today's topic is devoted to a common situation that has occurred many times in our practice. And for a big part of test engineers who are starting their vibration testing experience, vibration tests are mostly limited to sine, random, and shock. The three basic tests are indeed essential and cover a range of vibration testing needs. However, they are not exhaustive, and it is important that test engineers are aware of other vibration test options, which may sometimes be a better fit.
Yeah, that sounds about right, but sometimes you can hear from engineers that whatever is working, you shouldn't improve. So is a common situation that people use sine, random, and shock in their most basic versions for years, and they don't really feel like there is a need for any further exploration or extension. What would you say to that?
Yeah, well, sometimes three basic tests are really sufficient, specifically in situation when someone is running tests of serial production in a standardized procedure according to industrial standards or internal factory methods. However, if you are doing research or development work or can influence the testing procedures designed for your products, you might want to take a different approach and explore the whole spectrum of vibration tests available.
Mm-hmm. Okay, so let us introduce the method we suggest a user should go about. So if you are someone who feels like they want to explore more than the basics, what do ruler engineers suggest?
Well, if you are already a ruler client and you have sine, random, shock, then we see it reasonable to start with those options which can be used for free or with a minimum investment if you already have this option. So today we offer you to start with exploring the advanced features of basic sine, random, and shock. So while the webinar, we will draw your attention to such features as stepped sine, force control, resonance search track and dwell, notching limits. In random, we will talk about spectrum import, kurtosis, FDS, notching, and in shock test, we will discuss shock response spectrum.
I'm sorry. Do we have questions? Let us check. I think.
Okay. Just 1 second.
Okay, I can see that some people say that the sound is not very good. We will try to maybe adjust the microphone. And I forgot to tell you. That you can ask questions at any point of our presentation. So if a question occurs, don't hesitate to send it in the box. We will either answer as we go, or we may answer at the end or in the follow-up. So I hope the sound is good now. We'll try to adjust the microphone. If there's still trouble, please let us know.
So let me continue and start with the sine test type. Well, for many of you, these features may seem pretty common, as we actually talk about them a lot, and at our YouTube channel you can find videos to such topics as resonance search track and dwell, and we also discussed notching limits. However, today we want to make a refresher and tell you a little bit more about them. So I suggest starting with stepped sine. So stepped sine is a special feature inside Sine Test, which is available for free if you already have Sine, and allows going through the whole profile with frequencies. Now let's open our TestUp software and look where it can be found and what is the algorithm of its work. So stepped sine can be found in test settings of Sine Test. And it is called step-by-step test. So let's open it and have a closer look. Here you can see time relations. The time of frequency holding at each step is specified in the step field, and the pause between steps is specified in the pause field. In the right side, you can set a logarithmic step if it is required. Otherwise, it will be linear. If it is logarithmic, the step is specified in octave parts, and if it is linear, in frequency units. So here you can set the step size. For example, it will be 2 Hertz. I would like to pay your attention that the step can only be a non-negative number, and to enable a step-by-step sweep, you should add the corresponding command to the test schedule. So let's open schedule and choose stepped sweep.
So am I right that this is useful for a more meticulous approach? So if you take all your sweeps step by step, you make sure that you can take rather small steps, right?
Yes. Using a stepped sine, you can apply small steps if this is the requirement of your project.
Yeah, I can see a question here about the step size. So it can be definitely under 1 Hertz. Can actually be customized. So we had various situations where, for research and development purposes, we had to do step size under 1 Hertz. So yeah, pretty small. Can we check if there are any other questions now?
Let me have a look. No.
Okay, so this one is covered. Okay, we can move on.
Okay, so let me tell you about the algorithm of Stepped Sine. So it is pretty simple. You set a frequency step. So for example, as we did it, it was 2 Hertz, or as you can see in our slide, it is 1 Hertz. And then the program takes the first frequency from your profile. So for example, 10 Hertz, holds it for the set time. In our slide, you can see that the step time is 1 second. So it will be hold for 1 second, then pause for the specified time. In the slide, it is also 1 second. So it will be hold for 1 second, then moves to the next frequency. So it will be 11 Hertz, holds, pause, then again 12 Hertz, and so on until it reaches the end frequency. So let's go to the settings again. Also wanted to tell you that if you set logarithmic step, it is specified in octave parts. And I want to show you what will be changed. So if we do it, then the step size will be in octave parts. Now let's move on to the next sine feature. So it is force control. And this feature is available for a small fee. Force control allows you to select the physical quantity in which the task profile will be recalculated.
Yeah, I just wanted to add that by fee we mean that there is an option of non-accelerometer connection among our option menus. So basically, you will have to have the possibility to connect non-accelerometers, and they include force sensors.
Depending on the units in which the sensitivity of the installed sensor is measured, you can select task dimension in the units of acceleration or in the units of force. So mostly an accelerometer is used for the testing and the value acceleration is selected. And in this case, all values in the task profile are specified in acceleration units and the graph is automatically redrawn. But if a force sensor is used, all values in the profile will be recalculated in force units, and the graph appearance will also change. So let me open TestUp software and show you it more closely. So this is where you can find task dimension. So in the right corner, you need to choose force. And what is important to remember is that you need to change the sensor's units of dimension in the channel's configuration. So let's open channels and click on Open Channel Configuration. And here you need to set force units for all of your channels. Next to it, you can also set the type of channel. So it can be linear, IP, charge, TATS. So we will set it as linear. Then we click on Apply. And we are ready to start. Another thing I wanted to pay your attention that when you use a control force sensor, the program checks the limits tab in your test settings and make sure that the start and end force values in every profile row respect the shaker's maximum allowed force. So let's check it. Apply. And here you can see that we did something wrong, and the program notes us about it. And if we untick it, so just an example, we can, okay, we need to change the channel number too.
Yeah, so I suggest that actually our users don't really untick it yet, and let the system check the correspondence of the values entered to the shaker in use, because this guarantees that your equipment will not be damaged, and that your test will run smoothly and the device under test will be preserved. So it's a safety feature. So if such a message appears, it just means that you need to adjust the units to the limits of the shaker you are using. Okay, is there anything else in the Sine subsystem worth mentioning? Any features that may not be used very often but are there?
Yes, another feature that may be useful for testing needs is notching. So this feature can be found in the Sine test settings next to the control tab. So let me open it. So what are notch limits? In a few words, they let you set both a lower limit and an upper limit for every channel involved in the test, including the control channels. Let's open limits, go to notch limits tab. And here, I want to show it for you as a new test. 1 second. Okay, so here you can find different types of limits. So you can set limit for the lower and upper limit. You can set limits in decibels. You can also use a table with limits where you can specify start and end frequency and start and end amplifier. So before the webinar, I practiced it and entered these numbers. So the start frequency can be from 15 hertz and 25 hertz. Entered start amplitude is 10 G and the end amplitude is 30 G. And the limits are set in the units of the channel. So that means if you are using accelerometers, the limits will be in acceleration, velocity, or displacement. If you are using force sensors, in force, and strain gauges in microstrain.
So right, that notching is a safety feature. In a sense.
Yes, absolutely. Notching can be considered a safety feature, and actually it is widely applied, for example, in testing of batteries, industrial robot arms, solar panels,
aerospace.
In aerospace, yes. So in every of these examples, the idea is to define a maximum allowable value at the lower and upper limits and let the system protect itself automatically. Now we want to dive deep into resonance search track and dwell feature, as we've got a dedicated webinar for that, which you can find on our YouTube channel. I just wanted to quickly refresh your knowledge and remind you about it. So basically, when you are doing vibration testing, finding resonances is a key step. It tells you how your structure will actually behave under dynamic loads. It allows to experimentally find the product's natural frequency. These are those dangerous points where even a small vibration input can cause the amplitude to spike dramatically. And once you know where those critical frequencies live, you can take action and either redesign the structure to push those resonances out of your operating range, or build effective damping systems to keep things under control. So that was everything we wanted to show you in Sine test. And now we would like to move on to random. In the random test subsystem, you can use the option of spectrum import. It is a function allowing you to transform a recording of your real-life data to frequency domain through Fourier transform, and then test the device test with it within the random test subsystem. It is an easy and fast way to go from a purely mathematical approximation to testing closer to the actual conditions of operation. Spectrum import is clear for you to use it without any additional investments if you are a ruler client. So when would you use this? For example, you recorded vibration during a drug delivery. Now you want to test your product under those exact conditions, and Spectrum import does that in a few clicks. So let's open it in TestUp software. So we need to select a random test type. Open test settings. So while it is uploading,
maybe we can check if we have questions.
Mm-hmm. I don't know, the system is in progress. I need to wait a little bit. Finally, we're here. So the Spectrum import button allows creating a test profile based on the imported valvex file. So let's...
the recording in the proprietary ruler format.
Yeah. So let's upload one. Here we can see that there are different types of import methods. So you can hold the peaks or choose average. There are also different window types available for you. So we'll say rectangular window. The number of lines will be less. So let it set as 7,000. Overlaps count, we will save it as it is. And now we can click on the Calculate Spectrum button. And you can see that the graph has changed. Now we import it. And our profile will be rewritten.
I think it's important that our users are aware that it is a standard feature, which is already there if you have random test, and it's very convenient. A very convenient way to bring your testing as close to the real life environment as possible.
Here, I suppose that the example file was pretty big, and that's why we need a little time to wait. Okay, we got it. Another random test feature, which is a great addition and can be found to Spectrum import, is FDS, fatigue damage spectrum. So basically, it selects the sections of the impact which cause the most damage, fatigue, to the device under test, and recreates it in a compressed way in the signal sent to the shaker. So let's open it. FDS calculator. The damage level is calculated using the Palm-Green minor rule. So count the number of fluctuations with a certain amplitude and then calculate the damage by the slope of the signal to noise curve. In other words, to perform an FDS test, we need to calculate fatigue damage based on the recorded data and then synthesize a signal which would produce the same damage but in a shorter time. FDS is recommended if you want to test the device under test to destruction, but do not want to run tests of long duration.
FDS is a dedicated module, so it's an option among Rule software options, while Spectrum Import is already there for use, right?
Yeah.
Can we see the comparison? Can we see the difference between those two?
Yes. So here you can see the comparison. Here you can see the comparison table among these two advanced features available in a random test. So let me first tell you about the difference between signal generation type. So if you apply spectrum import, then the signal will be generated based on fast Fourier transform, power spectral density calculation, and averaging of the calculated power spectral densities. And if you use FDS, fatigue damage spectrum, then the calculation will be based on Palmgren-Minor rule. Now, a few words between the difference of usage. So spectrum imports random profile calculation is based on spectrum calculation from valve-x file. So as Elena mentioned, it is a special format available in TestUp software. And FDS allows you to imitate a long time period recording using a shorter test.
So basically, it's a slightly different application.
Yes.
Okay, I think now we can move on to another feature, another very important feature of random test, kurtosis.
So let me open TestUp. Oh, we can use it. So another function which can make a difference if you're testing in random test is kurtosis. It is a paid option, but it's a relatively small investment, especially if it can add value to your testing experience. Kurtosis is the parameter which allows controlling the deviation of the actual random signal from the normal Gaussian distribution. When the kurtosis grows, the time spent of the peak levels also increases, which makes the test closer to harsh real operation conditions. A standard Gaussian random has a kurtosis value of 3. However, in real-life conditions, a lot of vibrations are characterized by signals with a kurtosis value higher than 3. Well, for example, if you think of a car on a rough road, a helicopter rotor, or an aircraft wing in turbulence, you see that the vibration signal often has sharp and sudden peaks. And those peaks happen randomly. They can be much higher than the average. And the fatigue damage potential of such vibration is much greater than that of a traditional random signal. Therefore, using a pure Gaussian random will actually undertest the structure. Adjusting the value of kurtosis offers an easy solution to this problem. By increasing the value, say from 3 to 5 or 6, you make the peaks higher and more frequent, just like in real operation. And this gives you much better correlation between your lab test and actual field performance. So if the kurtosis box is checked, the settings button becomes active and you can set up the kurtosis value and the adjustment coefficient. So I think everything is pretty, can be good seen at the presentation.
Can we check the questions box? Because, okay, if there are any questions at this point, please ask. Okay. All right. Thank you.
Well, now there are no questions, and we can move on to the notching limits for random. So as we said in Sine, notching may be considered a safety feature, allowing the operator to control the upper and lower limits of the signal acceleration she wants to impact the device under test. So if you want to avoid resonances, for example, on certain levels, notching is the tool to use. And in certain spheres like aerospace, notching has become pretty standard. However, there are still more applications where it could be used. The principle of setting the limits for random notching is the same as for sine notching. So the tab notch limits allow you to set the upper and lower limits by channels. And when you applied it, you can choose you can see the graph where there will be lines of upper and lower limits, just like in our examples, in our example in the presentation.
Is that all about random test that we wanted to say?
Yes, we have covered a random test, and now we will move on to shock test. And here we would like to pay your attention to shock response spectrum tool, so SRS. Now we often get the question, what is the difference between just calculating an SRS inside the shock test and running a full SRS test? Well, in a regular shock test, we first define the waveform, for example, a half sine, and the SRS is calculated automatically as a characteristic of that shock. In the SRS test, which is a separate test type, it is the opposite. You first define the target SRS table, and the software synthesizes a waveform that matches the spectrum exactly. And about the SRS test as a separate test type, we will tell you the next time.
Yeah, so when we talk about additional features that could add to sine random shock, like other test types, in episode 2, we will definitely be talking about shock response spectrum test. And here we'll just feature the tab within shock test. Yeah.
Yeah. So let me open TestUp software and show you how it could be set. So let's open shock test. And we need to click on test settings. And here you can see SRS table. So to enable it, you need to put a tick use SRS table, and here it can be configured. So for example, let me set 100 Hertz start frequency and end frequency 110 Hertz, start amplitude equals 1 and end amplitude equals 10 G. Then we go to the SRS parameters, and here we can configure analysis parameters. So for example, choose damping factor or Q factor. So we choose here damping factor. The synthesized types, they're also different. Octave series, SRS frequencies, linear step, and we'll leave it as octave series. And we can apply it Okay, and get this type of the graph. So this was the final advanced feature we wanted to show you today during this webinar. So let's move on to the conclusions.
Yes, so basically what we wanted to demonstrate here is an easy way to move on past the basic sine, random, and shock in the method of exploring, like diving deeper in these exact software modules. So we have a firm belief that such features as stepped sine or force control in sine, notching in sine and random, spectrum import and random, FDS, and shock response spectrum calculation should be more familiar and more widespread. So we're hoping that this little lecture, this little overview, will be actually helpful and will be of use for your testing practices. As we said, it's a big topic, so moving from basic tests to more advanced can be taken further. So what we're going to do next month, we're going to write the run next episode of this webinar, where we'll be talking about the software modules you want to consider right after you have mastered sine, random, and shock and the little features within them that were the topic of today's webinar. I hope it was interesting and worth your while. If you have questions, now is the right time to send them to the questions box. So we'll be online for a few more minutes in order to answer your questions immediately. But if not, and if you have questions after or any feedback, any follow-up, we will be very happy to hear it. So as usual, we will follow up today or tomorrow. And we're hoping to hear your feedback and your questions, and we will make sure that our test engineers answer every question or concern. Thank you very much for your attention. Thank you for joining today, and it was great to have you.
So now we are